Hi everyone, welcome to Calculus 1 class. I'm Professor Lee. We are going to learn two big concepts of calculus called the derivative and integration this semester. Both of their definitions are derived from the limit process. What is the limit process? That's what we're going to learn in chapter 1. Here we go. 1.2 Finding limits graphically and numerically. In this section, we are going to find the limits of a function by either sketching the graph of a function, which is called then finding limits graphically, or we're going to create a table of values for f of x as x approaches to a given value from both sides, which is then called finding limits numerically. So here is an example. It says, sketch the graph of f of x equal quantity x squared minus 5x plus 6 over quantity x minus 2. What kind of function is this? Yes, it is called the rational function. Okay, so right below there, it says evaluate f of 2. Can we? So if I were to plug 2 for every x I see, I get 2 squared minus 5 times 2 plus 6 over 2 subtract 2. 2 squared is 4 minus 5 times 2 is 10 plus 6 gives me 0 over 2 subtract 2 is 0 as well, which is undefined. So we can see f of 2 does not exist. Let's do the algebra review. So from algebra 2 or college algebra that you learned, what happens to a rational function on x value such that you get 0 over 0? If you were to plug a certain x value and your function become 0 over 0, your rational function had a hole at that x. So when you get a 0 over 0, you get a hole on the graph of a rational function. And if you have a number over 0 and the number on the numerator is not 0, then you had a vertical asymptote at that x. Okay, so in this case, at x equal 2, you can see you're going to have a hole in there. So let's go ahead and factor the numerator here. So if you factor this rational function on the numerator, I need to come up with two numbers whose product is positive 6 and the sum is negative 5. Can you give me two such numbers? Yes, that will be negative 2 and a negative 3. So here is x minus 2 times x minus 3 over x minus 2. So we can cancel this as far as x is not equal to 2. And we know that this function is then same as x minus 3 graph except at x equal 2. Because at x equal 2, we just said that this function as a whole. So let's graph x minus 3 graph except at x equal 2. So this function y-intercept is negative 3. Since I have a f of x equal x minus 3, it is a linear function. Slope is 1. Y-intercept is 0, comma negative 3. So I have a 0, comma negative 1, negative 2, negative 3. Slope is 1, which is rise 1, run 1. Rise 1, run 1, but at 2, it is undefined. We have a hole there. Rise 1, run 1, rise 1, run 1. So I have a line with one hole at x equal 2. This is what the graph of this rational function looks like. Okay, so what is the limit of this rational function as the x approaches to 2? Okay, so graphically speaking, what you need to do is, as the x approaches to 2 from the left, your function is trying to reach to this point, and that y value is negative 1. What about the function value tries to approach as x approaches to 2 from the right? If x approaches to 2 from the right, your function is going down, 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 and try to reach this point as well. And that y value is -1. And because from both sides of 2, the y values are trying to reach to the same number, limit does exist, and we say the limit as x approaches to 2 of f of x, which is x squared minus 5x plus 6 over x minus 2 is equal to -1. This is how we answer this question. So graphically, we can find the limit, and limit is -1. But wait a minute, there is a hole in there. Doesn't matter. So limit value is not same as a function value. It is the y value where your function is trying to reach. It is not the function value. The existence of a limit does not depend on existence of y value. Your limit could exist without having a y value or not. Okay? So now let's try to find the same limit as x approaches to 2, numerically this time. You can see the table. It is created for you this time, but you have to create the table on your own. So I'm trying to find out where is this function is trying to reach as x approaches to 2. So you're gonna have to locate the 2 in the middle of the table, and from the left you list numbers that are very close to 2, like 1.9, that's close, but even get closer. So you get 1.99, get even closer, 1.999. Now from the right, you start with a 2.1, get closer, so you get 2.01, get even closer, you list 2.001. Then literally you plug 1.9 to every x you see in your function, which means you're gonna do 1.9 square minus 5 times 1.9 plus 6 all over parentheses 1.9 minus 2 close parentheses. Make sure to put parentheses over parentheses on your calculator so that it does give you correct answer. If you don't put parentheses to start with on the numerator and the denominator, then you might get the wrong answer. So be careful with that. If x was 1.9 and you calculate correctly, you are going to get -1.1 as a result. What about if x was 1.99? You plug it in and you're gonna get -1.01. What if x was 1.999? If you calculate correctly, you're gonna get -1.001. Okay, so what do you think this y value is trying to reach to? -1.1, -1.01, -1.001. Where is it going? Yes, this function value is trying to get closer to -1, I think. Let's try from the right this time. Plug 2.1 for every x you see on your function. So that will be 2.1 square minus 5 times 2.1 plus 6 over parentheses 2.1 minus 2. If you do that correctly, you're gonna get -0.9. How about if you plug 2.01? You get -0.99. How about when you plug 2.001? Then you get -0.999. Where do you think these numbers are trying to reach it to? Again, -1. So numerically, you can still see from the table values, limit as x approaches to 2 of this function is equal to -1. Did you understand, guys? Here is limit notation. In mathematical symbols, limit as x approaches c of fx is L, which is read the limit of fx as x approaches c is L, or the limit as x approaches c of fx is L. Let's go ahead and do an example. Sketch the graph of f of x equal quantity x minus 4 over quantity radical x minus 2. We would like to evaluate the limit as x approaches 4 of quantity x minus 4 over quantity radical x minus 2. So let's do it graphically first time, and then we will do it numerically the second time. So first of all, let's evaluate f of 4. When I evaluate f of 4, I get 4 minus 4 over radical 4 minus 2, which is 0 over radical 4 is 2, so I get 2 minus 2, so I get 0 over 0. So f of 4 does not exist. And we know this function has a hole at x equal 4. Now, how do I graph f of x equal quantity x minus 4 over quantity radical x minus 2? It's not very familiar function, right? But if you think about it, this x is radical x squared, and 4 can be thought as 2 squared, which makes it difference of squares. Then you know this will factor as radical x minus 2 times radical x plus 2 over radical x minus 2. So then, as far as x is not equal to 4, we can cancel the common factor, and this would be same as radical x plus 2 graph, except at x equal 4. Except. So therefore, x cannot be equal 4 because we have a hole at x equal 4. So the graph of f of x is going to be exactly same as radical x plus 2 except at x equal 4. At x equal 4, we will draw a hole, but anywhere else, the function will be coincide as radical x plus 2 function. And because it is a radical function, you know we cannot plug any non-negative number for x. So smallest x value we can plug it in would be 0. So let's put x and y. So smallest number is 0, and radical 0 is 0. 0 plus 2 is 2. The next nice number we can plug it in for x would be 1. So radical 1 is 1. 1 plus 2 is 3. So when x is 1, y is 3. And the next nice number would have been 4. But at 4, what happens? If x is 4, I get radical 4, which is 2 plus 2, which would have been 4. But it is undefined at that point. So we will draw a hole at x equal 2, y equal 4. So here's a 0, 2, 1, 3. When x equal 4, it would have been 4, but because it's a hole, I will put a hole there. And then we will draw a smooth radical function graph with a hole at x equal 4. So graphically speaking, could you find the limit as x approaches to 4 of f of x, which is quantity x minus 4 over radical x minus 2? So you're going to have to go x approaches to 4 from the left. You follow your function, go Get closer, 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 closer to 4. And where is your f of x trying to reach? Yes, that value would have been 4. Then from the right of 4, as x approaches to 4 from the right, your function is also getting closer, 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 closer to what value? Yes, 4 as well. So limit as x approaches 4 of this function is equal to 4. Let's try to find the limit numerically this time. Here is my table, and in the middle of the table, I would put 4, since we're trying to find the limit as x approaches 4. So in the middle, you locate 4. Now, from the left of 4, we would choose a very close number like 3.9, and then we will make it even closer by choosing 3.99. We'll make it even closer by choosing x equal to 3.999. From the right, we will choose 4.1 and then get closer 4.01 and then even closer 4.001. Okay, so now each of these x value that you have chosen, you are going to plug it in for your function. So first one is we have to evaluate f of 3.9, which is equal to quantity 3.9 subtract 4 over quantity radical 3.9 minus 2, enter. And if you do that, you're gonna get 3.9748. Wow, very close number to 4, huh? So now try to plug 3.99 for every x you see into your function. And you're gonna get 3.9975. Wow, even closer to 4. Now 3.999, you get 3.997. So you know your f of x is trying to reach to 4 as well. What about from the right? From the right, if I plug 4.1, you should get 4.0248. Now plug 4.01 for x. You get 4.0025, very close to 4. Now if you plug 4.001, you get 4.0002. So this f of x value is getting very, very close to 4 from both sides. So therefore, you can conclude the limit as x approaches 4 of quantity x minus 4 over quantity radical x minus 2 is 4. There is a very important point to make in here. In order for you to conclude the limit of this function is 4, the limit from the left has to be equal to the limit from the right. You can see from this table, limit from the left was 4, and the limit from the right was also 4. And because they match, we can conclude that the limit of this function as x approaches 4 is 4. The last example, greatest integer function, also called step function. Have you seen a function look like this with a bracket with another line inside of a bracket? Let me remind you what the definition is. So f of x equal greatest integer function of x is equal to whatever the number the x is. In order for x to get out of there, what you need to do is to choose the greatest integer less than or equal to x. This is the definition. For example, what is greatest integer function of 0? That will be bracket 0. I could have a 0 here and negative 1 here and positive 1 there. So then What is greatest integer less than or equal to 0? So out of all the number who lives in this location, you choose greatest integer, and that will be 0, right? So greatest integer function of 0 is 0. When x is 0, function value is 0. What would it be now? F of 0.5. F of 0.5 is greatest integer function of 0.5. Again, I have -1 here, 0 here, +1 there. And 0.5 is around here, right? So what is greatest integer less than or equal to 0.5? So out of all the numbers that I shaded, you got to pick greatest integer. And integers are 0, -1, -2, -3, -4, -5, dot, dot, dot. Those are the integers. So out of all those, greatest one would be still 0. What is the greatest integer function of 0.9? Greatest integer function of 0.9 still would be here. So out of all the numbers who lives in here, greatest integer would be still equal to 0 because 1's not in there. So if you graph this, when x equals 0, y is 0, and for any other x value is still 0, 0, 0, 0 until when? Until you hit 1. What is greatest integer function of 1? What is the greatest integer less than or equal to 1? Yes, now it includes 1. So 1 is the greatest integer less than or equal to 1. At 1, it is 1. 1 comma 1. And what would it be f of 1.5? When x equal 1.5, again, greatest integer less than or equal to 1.5 is still 1. F of 1.999. This is still any greatest integer less than or equal to 1.999 is still 1. So 1, 1, 1, 1, 1 until when? Yes, until you hit 2. Because when x equal 2, greatest integer less than or equal to 2, it is 2. So it becomes 2 at 2. Until when? Until you hit 3. At 3, it's gonna be value 3. So you can see why this function is also called the step function. It looks like a step. Okay, let's calculate a few numbers on the negative side so we can actually graph on the left-hand side of 0. What would be f of -1? So what is the greatest integer less than or equal to -1? -1, right? This was a 2. So when x equals -1, it is a -1, and it's gonna continue until it hits 0. And at -2, it's gonna be -2 until it hit -1. So here we go. So we just got the step function. All right. So graphically, what is the limit as x approaches -1 of greatest integer function is equal to? So let's see. X equal -1 is right here. So if you approach to -1 from the left, you need to follow the function from here. Fx is approaching to this value, which is -2. And then as x approaches -1 from the right, f of x is getting closer, closer, closer to this value, which is equal to -1. Well, my left limit was -2, and my right limit is -1. And when your left limit is not equal to the right limit, then we say limit does not exist. Let's find the limit numerically this time. So here is the table. x is approaching to -1. So in the middle of the table, I have x equal -1. Let's look at the number line. It helps us understand better because it could be confusing with a negative number. That's what it looks like. This is -1.5. This is -0.5. As x approaches to -1, from the left, we choose -1.1 and then get closer, -1.01. Even closer, -1.001. Now, from the right of -1, we choose -0.9. And then we choose -0.99. Get even closer to -1, choose -0.999. So when you plug it into your function, remember, what is -1.1? It's here somewhere. So what is the greatest integer less than or equal to this number? What's the greatest integer you see? That will be this number. That's the closest integer from this shaded region. So that will be -2. What about when x is -1.01? It's still left-hand side of -1. So it's like this. Greatest integer less than or equal to -1.01. It's still -2. How about if x was equal to -1.001? -1.001 still lives left-hand side of -1. So largest integer less than or equal to that number is still -2. How about x was equal to -0.9? So -0.9 is here. What is the greatest integer less than or equal to this number? It is -1. What if x was -0.99? -0.99 is over here. Still, what is the greatest integer less than or equal to -0.99? I see that's still -1. What if x was -0.999? That's still right-hand side of -1. So let's say it's here. Greatest integer less than or equal to -0.999 is still -1. So you can conclude that your left limit is -2, and your right limit as x approaches to -1 from the right is -1. So therefore, limit of greatest integer function as x approaches -1 does not exist. That's the conclusion. Here is the key fact in the box. Find the limits from a graph. If a limit as x approaches c of fx equal L, then fx must approach L from both sides as x approaches c. Got it? So make sure that your function is approaching to a certain number from both sides as x approaches c. So let's do some example to see if we get this. And another important fact is this L has to be a real number. It cannot be infinity or negative infinity because that's not a number. So make sure it is a real number. Find each limit or function value from the graph or indicate that it does not exist. So first graph, I have a parabola looking graph with one dot. So what's f of -2? I go to x equal -2. I see there's a hole on the parabola, but if you go up above the x equal -2, there is a dot at y equal 3. So f of -2 is defined. It is that dot 2, 3. And so your y value for that function value is 3. How about limit as x approaches -2 of f of x? So as x approaches -2 from the left, your function is going down, 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 and trying to approach it to this hole. And this value of the hole, y coordinate is 0. As x approaches -2 from the right, your function is going this way, and it's trying to reach to that hole. And the y value of the hole is 0. So from both sides of -2, your function values from both sides are approaching to the same y value, which is 0. So therefore, limit exists, and it is 0. Let's look at function g this time. I have a y equal g sub x, and this graph almost looks like a square root function. Anyways, so what's g sub 1? So when x equal 1, I see a dot there. When x equal 1, y is 2. So g sub 1 exists, and it is 2. How about the limit? As x approaches 1 from the left, your function is approaching to this value, the red dot, which was y value 2. As x approaches 1 from the right, your function is trying to reach it to this red dot again, which is y value 2. So this case, limit does exist again, and the limit is 2. Third graph. Let's look at the h graph. What is h's of -1? When x is -1, I have a dot here, and it is y value 2. So h's of -1 equal 2. Now how about the limit? So as x approaches to -1 from the left, my function is going this value right there, that blue dot, which is 2. So left limit is 2. How about from the right? As x approaches -1 from the right, I need to follow function value from the right, and it is trying to reach that hole. And that value of the hole is -1. And since left limit is +2 and right limit is -1, we can conclude that limit as x approaches -1 of h of x does not exist. How about last function y equal f of x graph? What's f of 2? I came to where x equal 2 is, and I go up, 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 up. Oops, I don't see anything. I don't have a dot. So f of 2 does not exist, because I have no dots above or below of x equal 2. How about limit as x approaches 2 of f of x? So as x approaches 2 from the right, I need to follow the function, and it is going to infinity. It's not trying to approach it to a number. It is keep going to infinity. And as x approaches 2 from the right, I need to follow function, and my function is again going to positive infinity. And because infinity is not a real number, we say limit x approaches 2 of f of x does not exist. So you can see that having the function value at that point has nothing to do with whether limit exists or does not exist. And even function value and limit value could coincide, or it didn't have to. Lastly, function value doesn't exist and limit doesn't exist. So in summary, limit exists if the left limit is equal to the right limit and that limit is a real number, period. Limit of a function does not exist if the left limit is not equal to the right limit. If either the left limit or right limit or both are infinity or negative infinity, then also the limit does not exist. Clear? Let's do the last example. Sketch a possible graph of a function with the given properties. So f of negative 2 is negative 1. X equals negative 2, y is negative 1. So function f passed through this point, but limit as x approaches to negative 2 is 3. So my function value does not agree with my limit value. So I will have a hole there. Also, f of 3 does not exist, but limit as x approaches to 3 of f of x equal 5. Limit at x equal 3 exists. So at x equal 3, y is 1, 2, 3, 4, 5. We'll have a hole because f of 3 does not exist. And that time they didn't even give the function value. So there are so many ways you can draw the graph that has these 4 characteristics. But the point is because limit exists at x equal negative 2 and limit exists at x equal 3, I have to make sure from left of negative 2 and right of negative 2 are approaching to the same number, and left of 3 and right of 3 function approach to 5. So I'm gonna draw the smooth curve like this. But now the limit as x approaches negative 2 of fx is 3, and limit of f of x as x approaches 3 is 5. So this graph satisfies all 4. It doesn't have to look like mine. In part 2, you're going to learn the formal definition of limit, and we are also going to learn how to prove a limit of a function is a certain number by the formal definition of limit.